Hey, all you cool cats and kittens. Welcome back. This week, we're going to go through Lab 5, the weight-length relationships. So go ahead and open up your R code. If you haven't already, get that downloaded off Canvas, and we'll get ready to roll. Okay. So yeah, you want to go ahead and open up this Word document as well as your all of your code. So I'm going to go ahead and clean up my R. Just get things clean for us here. All right, so the development of length-weight relationships is traditionally a huge part of fish population analysis. So the information on how fish weigh compared to how long they are is really important information for a fisheries manager because it gives you some indication of the condition of a fish, right? And so because the relationship between fish weight and fish length is curvilinear, the data are typically log transformed to allow for linear regression analysis. So the final equation that we report in the following format goes like this: log 10 of weight equals A plus B times the log 10 of length, where W equals the weight, L equals total length, A is an intercept, and B is your slope. And so just here's a review of your common logarithms to give you some estimates. All right, so below are two figures for weight length data for walleyes collected from Milford Reservoir in Kansas during fall gill netting. On the left are the actual data, and then on the right are these log transform data. So what do we notice about the differences in the shapes of the two graphs? So right off the bat, for the raw data, we see that it kind of follows this curvilinear relationship where we've got some kind of starting to approach on exponential growth in weight as we top out around 400 to 450 millimeters for walleye. Then when it comes to the log transformed ones, we see that it kind of cleans up, tightens that relationship, right? And so it kind of minimizes the variation. So we have a nice clean line there with the exception of these 2 points. All right, so for the first exercise, we're going to use the data that we collected from River Pond to make a log transformed length weight scatter plot for gizzard shad. And then for using the data that we collected from the Tallgrass Prairie National Preserve's Pond 24, we're going to make a log transformed length weight scatter plot for largemouth bass. The CSV files are available on Canvas and are called rpshad.csv and tpnpbass.csv. Make your figures and retrieve your regression equations using RStudio for both species. And then paste your scatter plots for both species and include the regression equation and coefficients of determination, the R squared values, in the figure caption. Remember to submit your R code along with it with your answers. So whenever you submit a lab document for this class, you should be submitting your R code so I can go back through, figure out where you went wrong. All right, so the first question is, once you've made those regressions, what does the slope of the regression line tell you about the species? And according to your coefficients of determination, which species had the least variability in weight at any given length? And how do you know this? Which one had the most? All right, and then for the third part, I want you to give me the A values for a 250 millimeter gizzard shad, a 365 millimeter gizzard shad, excuse me, not the A values. I want you to give me the regression equation and coefficients for those estimates for a 300 millimeter largemouth bass. And then with which of these predicted weights are you more confident? Explain. All right, so we're going to start with some shad data. So here's the River Pond data set. So we're going to go ahead and read in that data frame. Dorcept.df is what we'll call it. We'll attach the factors. We're going to go ahead and log transform the data right away. And then we're going to plot mass by total length. Then we need to reattach the data frame because we just added 2 new relationships there. Now we're going to create a linear regression model of log transform mass by log transform total length, and we'll get the summary for the relationship. And so we see we've got our multiple R squared of 0.9235, adjusted R squared of 0.9172, our F statistic, and then a p-value is highly significant right there. All right, so what's the predicted weight for a gizzard shad that's 250 millimeters long? Let's go ahead and run this. Pew! Object M not found. What did I just do there? Hmm. One second. Anyhow, so you're going to go ahead and take those y values, your predicted, figure out what your predicted values are for each of those. Sorry, I'm not sure exactly why that's not running, what I did wrong there, but we're going to do edit, undo, edit, undo, edit, undo, edit. Oh, so you're supposed to take the regression equation and put it in there yourself. I see. I see. Okay. So whatever the m value is, so the m value is going to be your slope. So from that output, slope is going to be 3.01 times 250 minus a is your intercept, so minus 5.0866. We get y. Predict a is not bound. What in the Sam Hill? Okay, so there's our y estimate. 747 millimeters is the predicted. What if we change it to 365? Pew. Now we run y, and it gets bigger. How about 300? Pew. 897. So see how across that range it influences our predicted weight? So we did get increases, right? Which is good. I'd argue that that's a little bit high for a gizzard shad. I work with gizzard shad for my dissertation, but anyhow, not important. So we'll just assume that those predicted weights are okay. All right, so now we're going to load in the TPNP data set for largemouth bass, and we're going to generate a log transformed length weight scatter plot for largemouth bass. Retrieve the regression equation and the R squared value as well. So we're going to read that in, load the bass data, attach them. Okay, so use R to calculate the Fulton's K. So let's talk about Fulton K. Yep. So now condition indices. So condition indices quantify fish condition. So how much does a fish weigh for its length? They also are known as condition factors and are a measure of relative plumpness of a fish. So why do we measure fish condition? If fish are too thin or too plump for their length, it should mean something to you as a biologist. If it's too thin, are there too high of a density of a particular population? Is food limiting? Are there poor environmental conditions? If they're too plump, then food is abundant. Could we maybe increase the population density? Could the lake sustain more fish of that species? And so here are a few, three common methods used to analyze fish condition. So the first one, and one of the older ones, is called Fulton condition factor. And so Lagler in 1956 suggested the use of a coefficient of condition, denoted as KTL, in the metric system and C in English units. This coefficient of condition is also referred to as a Fulton type condition factor and is calculated as follows. So your KTL, your Fulton value, equals 100,000 times W divided by L cubed, where W is the weight in grams of the fish and L is the total length in millimeters cubed. Okay. Next up, we're going to do a relative condition index. Leckrén proposed the use of relative condition factor Kn calculated as follows. So Kn equals W divided by Wn times 100, where W is the observed weight and Wn is the length-specific standard for a fish in the population under study. And so, for example, this study by Swingle and Shell provided statewide Wn values for Alabama fishes. So those are often things that you go to a textbook or a paper with a table and you look up for a particular species, what those length-specific standards are. All right, recently, an alternative method for evaluating fish condition has become available for some fish species. This method involves the calculation of relative weight, or WR. It's calculated as follows. WR equals W divided by WS times 100, where W is the actual weight of the fish being measured. WS is the standard weight for a fish of that length. And so you take the actual weight divided by the standard weight for a fish at that length times 100. Standard weight equations are actually weight length regressions, which we studied in an earlier lab exercise. So standard weight tables are provided below for demonstration, and you should use the standard weights you calculated earlier in this lab exercise. Okay, so for exercise 2, calculate KTL and relative weight for each individual largemouth bass in the Gashouse North Pond and Pond 24 using the CSV called BASS 2014. You're going to calculate the mean and 95% confidence intervals for each pond separately. Then you're going to make two bar graphs, one for each condition index. So I want one for KTL and then relative weight, showing the means and the error bars for each year and paste them below. Then use a t-test in RStudio, refer back to lab 1 for that code, to determine if there's a condition difference between these two ponds. So use a 2-sample t-test assuming equal variances. You could perform a separate t-test for each condition factor below. Remember to submit your reproducible R code to me and with your completed assignment to support your answers. So what were your p-values for the 2 tests? And then, excuse me, is there a significant difference in condition between the 2 years? It doesn't matter what condition index you used. All right, so let's go back to our R code and go into this BASS 2014 data set. So we read it in, attach, okay, use R to calculate Fulton's K. So I've calculated Fulton's K for you. You just need to use R to calculate relative weight. So there's calculating Fulton's K. Now we're going to subset things by the different ponds. So we're subsetting by Gashouse North and by Palmer. We're attaching it. Go ahead and get the lower and upper. You guys have confidence interval code from previous labs. And so now we're going to do sum of K. We're doing a group-wise mean of your K, your condition factor by pond. And the data is these BASS 2014. And then we've got a 95% confidence interval. So now we're going to attach those again. And we're going to perform a t-test comparing mean condition. So your K or your relative weight of bass in Gashouse and Palmer ponds. So here's a t-test. Boom, we're using K this time. So there's a library using ggplot2. We'll pull that in. And now we're going to create a ggplot comparing pond name with Fulton's K. And so you can literally copy and paste this code and then change this K value to the WR to get your relative weight, right? Because we want to do this for both types of condition factors. All right, so that's the way the cookie crumbles. That's the code for this week. I wish you luck. Make sure you go back through these exercises and practice with the code, practice manipulating the code, changing which condition factor you need or which pond name you need to pull from. Yeah, email me if you have questions. All right, have a good one, everybody.